So thank you very much for the invitation and for giving me the opportunity to talk about this work. So I would like to provide you some examples of linear hyperbolic groups which cannot be realized as discrete subgroups into rank 1 groups or products of rank 1 groups. And this is joint work with independent works with Sami Duba and Nicolas Tolozan. Okay, so I would like to start with some examples of hyperbolic groups. So let me say that throughout the talk, when we mean that H is linear, we mean that as an abstract group, it's linear over R, meaning that it admits faithful representation into some general linear group over R. And when we say that a finitely generated group gamma is Gromov hyperbolic, we mean that its Kelly graph equipped with a work metric induced by some finite generating set is delta hyperbolic for some delta greater or equal than 0. So it means that if you see triangles, they are all delta thin. So the delta neighborhood of any of the two geodesics of the triangle covers the third one. Okay, and now some examples. Like the most simple examples of hyperbolic groups are 3 groups. And the next more complicated class are, of course, surface groups. So we mean the case of a closed or readable hyperbolic surface. And here's a presentation of that group. Again, why these are hyperbolic? They are hyperbolic because they act nicely on a negatively curved Riemann manifold. So in this symmetric space, the 2-dimensional hyperbolic space. Okay, and now the second class consists of uniform lattices in a rank 1 group. The rank 1 Lie group G, of course, they contain 1. And what we would mean by a rank 1 Lie group in this talk, we mean a group G which is isogenous with one of the following Lie groups, like either the special orthogonal indefinite group or the special unitary indefinite group or the symplectic indefinite group, or the exceptional rank 1 Lie group, which is denoted by F for -20. So that's simply connected, and it's the isometry group of a particular symmetric space, which is the octonionic hyperbolic plane. Okay, and okay, what we mean by isogenous, we mean that your group is not SON1 or SUN1, etc., but it's up to finite index and up to taking a finite normal subgroup, the same as a quotient of this by a finite normal, so on. So the symmetric space associated is either, so it's in this case, we get the hyperbolic space, the real hyperbolic space, the complex hyperbolic space, and here we take the quaternionic hyperbolic space. And here we have the hyperbolic plane over the octonions. And a fact that will be crucial later is that there is no totally geodesic embedding of that space of the last one into a quaternionic one. Again, it's only enough to consider the quaternionic because it already contains those two. And again, like if you have a uniform lattice, so gamma acts geometrically on the symmetric space, and this is negatively curved, so your group is hyperbolic. Okay, so But in general, there are many more examples. Like just to mention some more, we have C prime 1/6 small cancellation groups. I'm not going to precisely define, but okay, they appeared in Greystock. So we say that a final presentation satisfies the C prime 1/6 condition if, first of all, we take the set of relations closed under inverse and under cyclic permutations, and this would satisfy this condition if whenever you take two relations and you take the maximal initial segment of the two relations, this is the length of this piece is less than 1/6 of the length of the two relations that they share it. Okay, and these groups are Gromov hyperbolic by Greenliger. But something more striking about these groups is that they are also linear over Z. So these are linear over Z, and that's due to the work of Wise and Ager. So and just to give you an example, like you might take this one related group with a standard word used in small constellation theory. So for n quite large, let's say more than 100, then this group is a C prime 1/6, even more, and it's linear over Z. So this is a class of examples which, in fact, they embed as discrete subgroups into GLNR, like the previous one. Okay, and now let me give you two more ways to construct hyperbolic groups, and maybe here and right here. The one is the Bestrina-Payne combination theory. So I'm going to give a particular instance, a particular consequence of the theory, which is about cyclic amalgamation. So if gamma 1 and gamma 2, and let's say torsion 3 hyperbolic groups, and let's fix WI, a maximal cyclic subgroup in each of them. It's enough to be in one of them, but is maximal cyclic. So, in terms of inclusion maximal, and then the amalgamated product of gamma 1 with gamma 2 by doing W1 with W2. So this is like simply the quotient of gamma 1 free product with gamma 2 over the normal closure of this work if this group is hyperbolic. So you can construct out of two hyperbolic groups a new one, which is the amalgamation. And in fact, these groups here might have much more different properties than gamma 1 and gamma 2. So it could happen that gamma 1 and gamma 2 are linear, but the amalgam is not.
Maybe to follow, please remind, there were some other non-linear examples, right?
Yes, that's the next theorem with the quotient here. So, yeah, the comment is that, like this group might differ a lot from gamma 1 and gamma 2 in general, depending on how pathological the gluing here is. Okay, so we like, with Nicola Tolosano, we constructed non-linear hyperbolic groups in that way from lattices in SPN1.
Just my question was before your example, maybe could you remind us, previously also there were some other
Yes.
examples, right?
Yeah,
Now you construct a new class of nonlinear.
right, yeah. The previous one were due to couple, it's the first ones, like in 2005. And yeah, so it's like on on the next here like one other way to construct hyperbolic groups is by taking quotients of a hyperbolic group. So like that many quotients of hyperbolic groups are hyperbolic and being hyperbolic. So in fact it's a theorem due to Gromov. On Sansky and the Zan. But if you have if delta is a non-elementary hyperbolic group, by non-elementary we mean that it's not virtually cyclic, and W is an infinite order. Then the quotient of delta by the normal closure of powers of W. So that's the normal subgroup generated by W to the n. Then this quotient again hyperbolic for all but finitely many values of n.
You adjust by one element, yes.
Even more, maybe even bigger, more than a singlet in here. So yeah, that
This is rather maybe a lemon, or what is you attributed to Gromov, Shansky, and Zan. So what is really remarkable in this work that you can quotient simultaneously over powers of a given element, right? To get girl side groups, but you cite not a girl side quotient, you cite just for one element, right?
yeah,
So
it's a finite.
maybe I would rather call it lemma, but
Yeah, and like this method here was used by Kapovich to give the first examples of nonlinear hyperbolic groups. And when we say nonlinear, not only linear over R, but over any field. So this was used for constructing nonlinear hyperbolic groups. And like one should start with a quaternionic lattice, so that means a lattice, a uniform lattice in SP n, 1 for n greater or equal than 2. Okay. All right, so that's some class of examples and some ways to produce hyperbolic groups. And now I would like to introduce a lot of groups because I want to formulate the question that motivated this work. So are there any questions? So a lot of groups are also linear, like the way we are going to define them, we will assume that they already lie into some special linear group. So they were introduced first by Labouri in 2004. Like the notion was given for surface groups, but the notion makes sense for every hyperbolic group. So the definition was later extended by Guissard and Milhard. And okay, so now we assume that gamma is a finitely generated group, not hyperbolic, and we equip it with a left-ward invariant metric. It's a finitely generated group. And let's assume that gamma, suppose gamma is a subgroup of some special linear group over R, and I find it is generated. And suppose that we are given an index between 1 and d minus 1 and fix. So we say that gamma is the inclusion of gamma is k and also if there exists a constant c and m positive, so that we have large gaps between singular values between elements. So we want, in fact, to have the ratio between the k singular value of an element over the k plus 1 singular value to grow uniformly exponentially in the word length. So that's the distance of the element from the identity. So that's for every gamma. Okay, so I didn't define what is the singular value, but let me do it here. Here, so you have a matrix. You can always take the product of G with the transpose matrix. So that's a symmetric one, and therefore it's diagonalizable with positive eigenvalues, and we list the eigenvalues in decreasing order. So the first one will be the square of the first singular value, the second one will be the square of the second singular value, etc. So for a group to be k and also we will require the ratio to grow uniformly exponentially in word length. And in fact, the examples like surface groups and all uniform lattices in any rank 1 Lie group, they do admit an Anosov representation. And okay, so we didn't define the notion for a particular semi-simple Lie group, but you can consider an embedding of your rank 1 Lie group into SLNR, and like automatically when you restrict to the lattice, this is satisfied for some k, and the k depends on the embedding you choose. Okay, and now I can formulate the question. Actually, there are two questions. So the first question is, we don't know if there exists some linear hyperbolic group which does not admit discrete faithful representations over R. So a linear hyperbolic group without a meaning for every D. And the second question is that we also don't know any example of a linear hyperbolic group without an Anosov representation. So, without into any special linear group. So there are some like small cancellation groups do admit discrete faithful representation, so they could not be answers under examples here, but we are not aware if they do admit an Anosov representation. At least, I mean, okay, surface groups are small cancellation, but for the more generic small cancellation groups, we are not aware if they do have unknown bearings. Okay, and these are the two questions that motivate the results. And now I can start giving you the results. How much time do we have?
20 minutes.
Analyze. So the first result gives you some new linear examples of hyperbolic groups constructed out of an awesome group. So suppose that gamma is a torsion-free anorthotic subgroup. So we didn't define the general notion into any semi-simply group, but we mean a particular case that you can think about is the case where these S and P are, and gamma is K anorthotic. So suppose that we have such an anorthotic group and fix and a maximal cyclic subgroup. And fix a maximal cyclic subgroup. Then the following HNN extension is linear. Then, so that's the group where we take the free product of gamma with Z, the stable letter, and we mod out by this word here. We want the stable letter to centralize W. Then this group admits a faithful representation into G. So this is not hyperbolic because it contains Z squared, but it contains lots of hyperbolic subgroups. So the double of gamma log W is inside here. So so the double is in. So in the case where gamma was a quaternionic lattice, like a lattice in SP n, 1, this group was not, before that we didn't know if it were linear, but it turns out to be linear. The double. And let me say here that the assumption that gamma is anorthotic is essential. If gamma is a non-hyperbolic group, for example, SLDZ, like a uniform lattice, a high rank lattice, d greater or equal than 3, this group might fail to be linear. So it's essential that we have the anorthotic assumption here. And also it's essential that we get linearity over doing the same copy of W. We discussed what in the beginning of the talk what could go wrong in general. Okay, so that's the first result. Okay, now by using this we can in fact provide linear hyperbolic groups which are indiscrete in rank 1. So suppose that delta is uniform, M is greater or equal than 4, and torsion free is a uniform torsion free lattice, and W a maximal cyclic subgroup, non-trivial, of course. Then the W first admits a faithful representation into SPN1, n,1. But at the same time, does not admit a discrete faithful representation into rank 1 group. So, discrete faithful. So the first class of examples are constructed by doubling quaternionic lattice along any maximal cyclic element. Okay, and for the proof of the second part, while in the first one we use the anosovness a lot to prove linearity and the faithfulness here, for this we use the Corlet's Archimedean superrigidity. Okay, and now the third one. So the third one, now it provides even more examples of such groups, but in fact they fail to be discrete faithful, to admit discrete faithful representation of products of rank 1 groups. So this is in joint work with Sami Duba. But for this one, we have to use lattices in F4 -20. So we use lattices in the exceptional rank 1 Lie group. And the statement is as follows: suppose that gamma suppose we're given two uniform lattices, uniform lattices. And we assume that M is quite large. So in fact, let's assume it's at least 51. Then the free product so the free product of these two lattices is again a hyperbolic group, does not admit discrete faithful representations into any Lie group isogynous to maybe a product of rank 1 groups. And moreover, it does admit a lot of representations. So it admits a one and also, in fact, it's the most general kind of anosov representation that one has into SLDR for some D. So very large. And again, for the proof here, we use the superrigidity results for that we have for the lattices in F4 -20 and SPN, 1. Let me mention that for the doubles here, we don't know whether they do admit a lot of representations. So we don't know whether they are in fact maybe they are good candidates for answering the second question. Okay, now in the last 10 minutes I have, maybe I can describe why this free product is not cannot be realized as a discrete subgroup in products. And for this, we will use the following lemma, which is a consequence of superrigidity. Unfortunately, I don't think I have the time to discuss the statement of superrigidity, but at least I can record here the lemma. So using superrigidity, which is due to correlating Archimedean planes, the norm of soil in the non-Archimedean case. So the first part is that if gamma is a lattice in F4 negative 20, and every representation of gamma into a target Lie group, which is SPM, 1, it has compact image. So every such representation has three compact images. So compact closure. So that's quite a strong statement. And the second is that if n is quite large, and we have a lattice in XPN, 1, then every representation has finite image. Not only pre-compact, but it has finite image. Okay, and now how this lemma would imply the fact that this free product is not discrete in rank 1 in products of rank 1 groups. In fact, one could exhibit explicit sequence that remain bounded under any linear representation in that case. So proof. In products. So again, suppose that we look at representation, let's say rho of gamma and delta into a product of rank 1 Lie groups. We know these all are isogenous to one of these 4 families there. So in fact, okay, we said that this is we said to every group that is isogenous to a product 1, but in general, up to passing to a finite index subgroup of this free product, it's enough to consider only the case of products of SON1s, SUN1s, SPM1s, or F4 negative 20. So in fact, we can split the factors into 2 families, the ones that are all isogenous with F4 negative 20, and the ones that are all isogenous with something that embeds in SPM, 1. So here we assume that all these groups embed in SP n, 1 for some n quite huge. Okay, so by the lemma, what do we know? Like gamma is a uniform lattice in F4 negative 20, so we know that the projection of rho gamma is pre-compact when we project to these factors here. So it is bounded here. And we know that the image of delta, the projection of the image of delta into these factors has finite image in each of them. So one could pass to a finite index subgroup deep enough in delta to assume that in fact this image is trivial here. So up to passing to delta prime of finite index normal in delta, the projection of rho delta is trivial in the first set of indices. So, okay, and now what you can do is that you can take an infinite sequence in gamma, and you take any element you want with this delta prime, and then you look the image of the commutator of gamma n with delta. Okay, so that's to see exactly what is this. This is so it's the image of these elements here. Well, if you project into the F4 negative 20 factors, this is going to be the trivial world because delta is trivial. And in the other factors, it all remains bounded because gamma n is bounded. So you always have a sequence which remains bounded. And yeah, that's of course an infinite sequence in the free product. The proof of theorem B, the indiscreteness in theorem B uses the correlated superrigidity theorem, and it has to do with the fact that if you have two quaternionic hyperbolic subspaces of a bigger quaternionic hyperbolic space, and they intersect on a line, they have to intersect in the unique quaternionic line containing that binding geodesic. So that was my last remark, and yeah, I think I will stop here.
Okay, questions for the speaker? Sorry.
Your bound m larger than 51. That's
You mean the M? Here, yeah.
Yeah, it's also on the top of that.
Yes.
Why is 50? Why 51? Big number.
Because we consider F4 negative 20 embedded in GL52C. Like we see that as a reductive subgroup of GL52C, and 51 turns out to be the correct number, so that the quaternionic hyperbolic space of that dimension does not admit a totally geodesic embedding in the symmetric space of GL52C. So, but you can reduce it
Probably is and not on SP21 and then in that 4 minus 2.
in F4 negative 20. Yes, it does.
But other shouldn't.
Probably has to do with the smallest real dimensional representation of F4 negative 20, maybe complex. Yeah.
That's a very general question. So I guess until now, nothing new about not residentially finite hyperbolic rooms. So all known constructions really give some residentially finite, right? All non-linear, on non-linear like Kapovich's construction, right? So is it true that all construction we know to produce something non-linear hyperbolic? Still,
If they keep residually finite?
no, it's not clear. What's the
It's not needed. By example, if you take the non-congruence, if you amalgam two lattices in SP and one in SP, one along something that is non-congruent in SO in I mean, we don't know the congruent subgroup property for SP and one. So there are subgroup that if the congruent subgroup property is true for SP and one, won't be separable. So along the non-congruence.
So even for such groups, it's challenging. Even for such groups, it's challenging to take the assignments.
Oh, sorry.
To check, excuse me,
Residual affinities.
I think we only know for some amalgamations along Z, like, but not, but like, we don't know if we double along a free group or like quaternary lattice. We don't know if this group is residually defined because we don't know if it's a separable free subgroup. Can be, it's non-linear, but.
So I think the answer is most examples of nonlinear groups, we expect them to be not
I mean,
really
your
defined.
examples, I think, all the
We
examples
have-
are really
We have examples of nonlinear reasonably finite groups, and I think
Yes, but I mean,
they are the first.
before you go, I believe before you go, the examples like of Karpovich, they are really known to be reasonable.
No.
No, but they will take.
They are I think they are expected to
No, they
be
will-
non-reasonably finite.
Not really, but didn't appear with groups who had a paper long ago. I thought they were showing the some of Karpovich examples are reasonably
I
finite.
think,
You know the
so
paper appear in the groups,
I
right?
don't, but I think there is a question of math overflow. Someone asking what is an example of a nonlinear reasonably finite group? And there is an answer by Mark Sapir saying, I would really love to know.
Yeah, this is a famous question, so, but.
The question is, what is an example of a nonlinear residually finite group? And Mark Sapir answers, I would love to know.
In which year, because he really, but I need to check, because I remember that I don't know, it's with Carnelli, but maybe after.
They have
Ah, yes,
a
it's
paper
called
on one.
No, sorry. It's a nonlinear hyperbolic. Yes, they have a work with two of, they have examples of nonlinear.
And then the
But no, with both, they are not hyperbolic. They have examples of nonlinear residue finite, but not hyperbolic.
They're one related.
And the construct, you mean, even in the construction of Karpovich, it's also not clear.
All right, are there questions from anyone on Zoom? And just a reminder, you can also unmute yourself and we'll hear you in the room. All right, let's thank the speaker one more time.